Assalamualaikum. Okay, in this video, I will give example 9, which this example is for overall heat transfer coefficient. Previously, we already learned about the overall heat transfer coefficient equation and then a fouling factor. Now I will focus first in this example about overall heat transfer coefficient. So let's take a look at the question. So this is the question. So hot oil is to be cool, okay, cool in double tube counterflow heat exchanger, okay. So we have double pipe heat exchanger problems here, and then the copper inner tubes, okay, have diameter of 2 centimeter and negligible thickness. So at this point, previously I've already mentioned you, if in the question mentioned about negligible thickness, what you will do is to assume that there will be no conduction in this tube, in the tube. So here, the question specifically mentioned that the inner copper tubes negligible thickness. Therefore, the conduction from the tube, inner tube to the outer tube can be neglect. Okay, it means that we have inner tube and there will be another tubes outside, and the thickness of these tubes is negligible. So therefore the conduction process at this point will be neglect. Okay, and the diameter, and other than that, at this point we can say that di is equal to d out, because no thickness, negligible thickness, we may assume that inner diameter is equal to outer diameter. Therefore the surface area for inner also the same as surface area for outer. This is specifically for inner tube. Okay, it is not for outer tube. Inner tube, which is made by copper. Okay, the inner diameter of the outer tube, which means the bigger tube. We have inner tube, and then the outside of this we have another tube. This tube, outer tube, the diameter is 3 centimeter. So d inner, so here is di is equivalent to 3 centimeter. Okay, water flows through the tube at a rate of 0.5 kilogram per second. Okay, flow rate in the tube, because here mentioned water flows through the tube. The smaller tube is tube. Okay, the bigger tube, the outer tube, is what we call as a shell. So if you have double pipe heat exchanger, the outer is what we call as a shell, and the inner is tube. Okay, shell and tube. So outside of this is shell, and then this is tube. So when this question states that water flows through the tubes, means that the water flows through the inner tube, okay, at the rate of 0.5 kilogram per second, and the oil through the shell. Okay, shell is the outside, the tube outside. We have annulus here. So previously I've mentioned that this annulus I will explain more in the heat exchanger topic. So I will explain about this annulus calculation. If you get the turbulent flow, it will use the same equation as what you same equation. But if you get the developing laminar flow, then there will be something different. You have to refer to the tables to get the value of Nusselt number. Okay, later on you will understand about this. Okay, taking the average temperatures of water and the oil to be 45 degrees Celsius and 80 degrees Celsius, respectively, determine the overall heat transfer coefficient of this heat exchanger. So at this point here, taking the average temperature, here the average temperature represent the film, okay, average temperature for the water and oil. So we can directly reverse the temperature of water and oil at 45 and 80 degrees Celsius. So therefore you have to see and you have to go to the table E9 and refer to 45 degrees Celsius for water and 80 degrees Celsius for oil. And you take out the info on diameter, density, thermal conductivity, Prandtl number, and kinematic viscosity. Okay. So for the annular space, so we know that there will be an annular space here, where the space in between inner and outer surface. So we have annular space here, annular space here. So at this point, when we calculate the Reynolds number at that point, at that shell site, so what happened, and when you get the value of Reynolds number is below than 2300, so that is falls under the laminar flow, and normally we are assuming that that is developing laminar flow. So when that happens, the Nusselt number for that condition will be determined, okay, by using this figure. So this figure is only for developing laminar flow, okay, developing laminar flow for annular space, okay, annular space. So how to see this figure? So when you refer to this Nusselt number I when tube is heated, refer to this value when tube is heated, okay. Whereas for another one is tube is cool, okay, tube is cool. This is the easiest way to understand about this value, okay. There will be another definition on how to another clarification on how to refer to this figure, and I found out that this is the simplest and the most simple way to to tells you that this value is for what, okay. So when you calculate Nusselt number, and then when you calculate the Reynolds number, you get the value of below than 2300, and then we assume that that is developing laminar flow. And after you assume developing laminar flow, you go straight to this figure, table 11.3, and try to find di over do, inner over outer, diameter inner and diameter outer. This is for the outer tubes, okay, for the shell side. So we have here, this is inner diameter and then the outer diameter, inner tube and outer tube. This outer tube is the shell side. So this is di and this is do, okay. Okay, this is di and this is do. So you will find what is the value of di over do, this ratio, and then tube is heated is you will refer to this tube, okay. The outside is shell and then this is tube. So what will happen to this tube? If your shell side much more hotter than the tube side, and you understand that that is the process of heating, so the heat will transfer into the tubes. So if the heat transferred to the tubes, therefore the tube is heated, then you will refer only Nusselt number I for the values of Nusselt number. Okay. For example, you get 0.1 di over do. Okay, and then your Nusselt number, and you found that the tube is heated, therefore you will directly use this Nusselt number. Okay, 0.1 and 11.56, and your Nusselt number is 11.56. So you will directly use the Nusselt number given in this table. Okay, that is only the condition where the developing laminar flow exists for the annular space. If you are happens to calculate that the Reynolds number is under the turbulent flow, fully turbulent flow, then you have to use the turbulent flow equation. Okay, let's take a look on how to solve this question. So first of all, what you have to do is you have to understand what is the aim for this question. The first one is determine the overall heat transfer coefficient of this heat exchanger. So we have to determine what is the value of U. So here we have to find what is U, overall heat transfer coefficient. From previous video, we know that to find U is 1 over U equal to 1 over Hi plus 1 over H out. Okay, Hi is inner and O is outer. So now we have a double pipe heat exchanger question. Okay, for double pipe heat exchanger, we know that previously we already learned about the external force convection, and then internal force convection. So we have to determine where the value of Hi here and the value of H out here. So it represents H out. Actually, this is inner. Okay, we have to determine each of these H. So how to determine this H? We will refer to this condition. Okay, either it is external force convection or internal force convection. Now for the double tube heat exchanger, the inner tube will have internal force convection. What about H out? H at this fluid, for this fluid. So H out here also internal force convection. So why do we have to determine either it is internal force convection or external force convection? Because each of these force convection chapter has different equation that needs to be used in order to find what is the Nusselt number. So under internal force convection, so we have to determine where either it is developing laminar flow or what? Fully developed turbulent flow. Okay, same here, developing laminar flow or fully developed turbulent flow. So you have to check on the equation for internal force convection. So what about external force convection? Let's say you have a pipe. Okay, this pipe is exposed to the ambient where the air is at 30 degrees Celsius, and then the flow of the fluid inside is water at 15 degrees Celsius. So now you have H out and here is Hi. Okay, this Hi is internal force convection. What about H out? H out is external force convection. So here we have tube inside the tube. Therefore, this H out is considered as internal. Okay, that's why for the double pipe heat exchanger, we will consider H value. We will calculate H value from the internal force convection equation. So now we have to calculate what is HI and what is H out. So HI is the heat transfer coefficient for the tube. Okay, so let's take a look at the first H, which is HI, because we want to determine what is the overall heat transfer coefficient. So the hydraulic diameter, first we have to determine what is the Reynolds number. So we know that Reynolds number, the equation is VD over K. Okay, VDA, D is DH, hydraulic diameter. Now, if you are dealing with a circular tube, then DH will be D, okay, over K. D is DI lah, okay. Now, DI is already been given. Sorry, not K. VDH over V, kinematic viscosity, not K. Okay, kinematic viscosity. So, DI is already been given in the question. Kinematic viscosity is you already found in the properties table. What about the velocity? So, we have to find what is the velocity. In the question, we already been given with the values of mass flow rate. Mass flow rate of fluid inside. Mass flow rate of waters is 0.5. Therefore, M flow rate is equivalent to 0.4 kilogram per second. So from mass flow rate, we are actually can find what is the velocity. So by using the equation, mass flow rate equal to rho V A. So rearrange this equation, V equal to M dot over rho times with A. So A here is a cross-sectional area. Because we are dealing or we are calculating mass flow rate, we are not calculating heat transfer rate. We are calculating mass flow rate. Therefore, A here is a cross-sectional area. Because if you are calculating surface area, you will use pi dl, since you are calculating surface area. This is normally for heat transfer rate. Okay, whereas for the AC, cross-sectional area is pi d squared over 4. Okay, this is normally for mass flow rate or discharge or volumetric flow rate. Discharge and volumetric flow rate is the same. Okay, so now we have to find what is the velocity. V here is a velocity. So V equal to 0.5 divided by density is 990.1 times with by d squared over 4, 0.02 over 4. So you will get your value for velocity is 1.61 meter per second. This is the velocity of water in a tube. Then we have to calculate what is the Reynolds number. Substitute the value of velocity in the equation of Reynolds number. So Reynolds number equal to, okay, V is 1.61 times with 0.02 divided by 0.602 times 10 minus 6. Okay, you will get the value of Reynolds number is 53,400 490. So that is your Reynolds number. Now, for the internal force convection, after you determine the Reynolds number, you have to determine whether it is under developing laminar flow or fully developed laminar flow. So for fully developed turbulent flow, you have to determine whether it is laminar or turbulent. And under internal force convection, we have two different categories or two different equation for different types of flow. First is developing laminar flow, and then the second one is fully developed turbulent flow. If your Reynolds number is much more greater than 10,000, then your flow is fully developed laminar flow. Then we have here 50,490. Therefore, I will assume that this flow is fully developed turbulent flow because the Reynolds number is greater than 10,000. Okay, this is fully developed laminar flow because the Reynolds number is greater than 10,000. So under fully developed laminar flow, fully developed turbulent flow, we know that the equation is only one. Okay, Nusselt number is equal to HD over K equal to 0.023 Reynolds number power of 0.8, okay, Prandtl number n. Okay, this is the equation and the fully developed turbulent flow. So n equal to 0.3 for cooling, and then n is 0.4 for heating. So now let us determine whether it is a cooling process or heating process. Take a look at the question. Okay, water flows through the tube at a rate of 0.5 kilogram and the oil through the shell at a rate of 0.8. Okay, now we already been given with the average temperature. For the water is 45 and oil is 80 degrees Celsius. Now oil is much more greater in temperature value than water. Therefore, the heat transfer will be from the oil to water. Am I right? Oil is 80 degrees Celsius, average temperature, and then water is 45 degrees Celsius. Therefore, the heat will be transferred from oil to water. So water flows in a tube. Therefore, the tube will have heating process. Therefore, N here will be substituted with 0.4. Okay. Now your N, Nusselt number, equal to HD over K, 0.023 Reynolds number, power of 0.8, and Prandtl number 0.4. Now substitute all the values inside. You will get the value of Nusselt number is equivalent to 240.6. Now what you have to do is you have to calculate what is the heat transfer coefficient. This is our objective for the first H. Here is HI. So I change it into HI equal to 240.6 times with K divided by diameter. So substitute all the values, you will get HI is equivalent to 7663 watt per meter square dot Kelvin. That is your first HI. Okay, now we move to second H. So we already determined HI. Now second H is H out. H out is annular space. Okay, annular space. Where you have, this is in a tube, and then we have another tube. So this space is annular space. Okay, now we have to calculate what is the Reynolds number. So Reynolds number is V d hydraulic over kinematic viscosity. Now since this is annular space, therefore the dH is totally different. So you have to substitute. Previously we substitute dH as a di. Am I right? Here we substitute di value because that is tube. Okay, if you deals with annular space, dH, your hydraulic diameter will be dO minus di over mu. So your hydraulic diameter will becomes d out tolak di. So d out, the outer is this inner diameter is the outer, and then this is the outer diameter of the first inner tube of the inner tube is di. Okay, and then the inner diameter of the outer tube is dO. Okay, so to get what is the hydraulic diameter, dO minus di times with velocity over kinematic viscosity. Now we want to find what is the velocity at the annular space. So we already been given with mass flow rate, where the mass flow rate is equivalent to 0.8 kilogram per second. So again, we will use the same equation as before. So mass flow rate equal to rho dA. So A here is cross-sectional area. So V equivalent to mass flow rate over rho AC. Okay, now here we have a little bit different with the previous equation because this AC. So AC is pi d squared over 4. Okay, now we have annular space. So you have to minus the bigger size cross-sectional area minus the smaller cross-sectional area in order for you to get what is the cross-sectional area for the annular space, which means that you have AC equal to AC out minus AC in, which means you have to calculate the bigger area, cross-sectional area, and then you have to calculate the smaller tubes cross-sectional area. So when you are trying to subtract with these two areas, you will get the area of annular space. Okay, so that's why you have to do cross-sectional area by subtracting the outer area minus the inner area. So your AC will be pi d out square over 4 minus pi di square over 4. Now we have pi over 4. Okay, same. So we factorize pi over 4 d out square minus di square. So this is the equation for cross-sectional area. So calculate the cross-sectional area first and then substitute into this equation. So you will get that, so 0.8 divided by 852 times with AC. Please calculate the AC values and then substitute into this. So you will get the value of velocity that is equivalent to 2.39 meter per second. Now we already have velocity value, and then we substitute into the Reynolds number equation. So our Reynolds number is equal to 2.39 times with 0.01 divided by 3.794 times 10 to the power of minus 5. So you will get your Reynolds number is 630. So now 630 is below than 2300. So this is laminar flow. And we will assume that this is developing laminar flow. So assume developing laminar flow. Therefore, we will use the equation for Nusselt number to determine the Nusselt number under developing laminar flow. You know that if we are assuming that this is fully developed laminar flow and it has a constant value of Nusselt number is equivalent to 3.66. Therefore, we do not want to assume directly that this is the region where fully developed laminar flow occurs. Then, to simplify your method, you will assume that this is developing laminar flow. Then you have to use equation 3.66 plus you have to refer to this equation. But now, this is the condition where we have annular space. It is totally different when you have these kinds of problems where you want to find what is the H out inside the tank, kan? Right. So now it is a double pipe, and for the annular space, we have to refer this value, Nusselt number. Now we take a look at the Nusselt number, NUI or NUO. So now I already explained to you when you refer to this Nusselt number when your tube is heated. Now your tube is, yes, heated, not cool. Your tube, inside the tube is water, and the oil transfer heat to the water. Therefore, water will be heated. Okay, the fluid inside the tube will be heated. Therefore, we will refer to the Nusselt number I. Now, what we are going to do is we have to calculate what is dI over d out. So our dI here is 0.02. Okay, dI is 0.02 and our d out is 0.03. So you have to divide with these two values. So you will get 0.667. So you will get dI over dO is 0.667. So you have to refer to these two values. Okay. So this value is in the middle, 0.667. Therefore, you have to interpolate in order for you to get what is the value of Nusselt number I at 0.667. So after interpolation, I get the Nusselt number is equivalent to 5.45. So from the table. Now from here, we have to substitute and we have to equate with Nusselt number H D over K. Now this H is H out, so equal to 5.45. So after rearrange, you will get your H out is equivalent to 0.138 watt per meter dot Kelvin times with 5.45 divided by 0.01 meter. So you will get your heat transfer coefficient that is equivalent to 75.2 watt per meter square dot Kelvin. So H out. Okay. Now you already get your HI and H out. Then substitute into 1 over U equal to 1 over H out plus 1 over HI. Okay. So you will rearrange U is equal to 1 over H out plus 1 over HI. So substitute the value, you will get value for the overall heat transfer coefficient is 74.5 watt per meter square dot Kelvin. Okay. So I want to stress on this figure. This figure is only for annular space. Do not take the same method as annular space method to find Nusselt number and apply it to the other shape, okay? Because it is totally wrong. This is only for annular space where we have tube inside the tube and there is a space in between, okay? That is what we call annular space, okay? That's all for the example 9 to find overall heat transfer coefficient. Thank you.